Lesson 49 is on concavity, and the definition of concavity is how a graph bends. So we have concave up and we have concave down. Concave up is something that looks like this. It essentially opens up. Concave down would be something like this that essentially opens down. Concave up. The reason it's called concave up is because the function is up above the point of tangency. And I'll show you what I mean by that in a second. Because remember, we're talking derivatives here and slope, so we're going to focus on that. And then, speaking of slope, the slope is increasing. So the two important ideas with concave up. So what that means is this: the function is up above the point of tangency. So if this function up here is in blue, what it means is if I find a point of tangency right here, and my function is above that point. If I find, I'm going to make up a number for that slope. I'm going to say that the slope is a -4. If I find another point, so say this point here, I'll use a different color, and I find the point of tangency, again, my function is still up above the point of tangency. That slope looks like it's about -1. If I pick another point, say I pick this point, my point of tangency is still above that, and now I'll say my slope is -1/4. Just sort of making up these numbers as I go along. Now, when I go to the right-hand side over here, and if I find this point of tangency, this slope looks like it's about +1. And if I do one more, because this is going to emphasize my second point, let's say this slope is about 4. You can notice my blue, my function, is above all of my points that I have drawn. When I put in that line of tangency, that line of tangency is below my function. What you should also notice is that the slope is increasing. We go from -4 to -1. It's increasing. To -1/4, increasing. To 1 to 4. It's increasing the whole time. So that is if you have something that is concave up. Something that is concave down is just completely the opposite. The function now is going to be down below the points of tangency. Down, because it's concave down, below points of tangency. And you guessed it, the slope is going to be decreasing. So again, let's take a look at some points. I won't do as many this time, but if I look at this value right here, I'm going to say the slope is 4 right there. If I look at another point close to it, now my slope is 1. Notice it decreased 4 to 1. If I pick another point right here, now I'm going negative, and I'll do one last point right here. Now it's -4, so you can see that it was decreasing. And my function is always down below the point of tangency. So concavity is how a function bends, and very important in calculus in order to find the concavity, so to determine if it's concave up or concave down, what we're going to do is we're going to take the second derivative. So the second derivative is always going to determine our concavity, if it's concave up or concave down. Let's take a look at this function right here really quick. And I have a function right here. This part of my function is concave down because it looks like a parabola that opens down. So this is concave down. But when I look at this part right here, now it's kind of opening up. It's concave up. In between there, I have what is called a point of inflection. So this right here is called a point of inflection. And what that means is that that point of inflection is essentially a change in concavity. What I have in red is all concave down. that point of inflection suddenly changes, and then I turn to concave up. Now I would actually have another inflection point here because it looks like what's following is going to be concave down. So I would have another point of inflection right there, a change in concavity. So here's our rules of concavity. Because concavity is the second derivative, if we take the second derivative, and if that value is positive, so greater than 0, then we have something that is concave. Oops, spelling this wrong here. Concave up. Okay, so positive, it's concave up. If we take our derivative and it's negative or less than 0, then we're going to have something that's concave down. And the last thing is if we take the derivative and it equals 0, then what we have is that inflection point, a change in concavity. We're moving from concave up to concave down or concave down to concave up. So let's do a problem in which we're going to graph a function. And look what I'm giving you. I'm giving you characteristics about the function. And the first one says, if the derivative is greater than 0, meaning it's positive, then what we know about the function is, remember, the derivative is the slope. Then we know that the function is increasing. And why do we know that? Because if the slope is positive, a positive slope has to increase from left to right. The next one says the slope is less than 0, meaning the slope is negative. If the slope is negative, we know the function is decreasing. Now, if we see that if the slope is equal to 0, if the slope is equal to 0, it's flat, okay? What happens there is we have a constant. We have a turning point. Okay, it's constant, or we have a turning point. And if you look at the next one says second derivative greater than 0. So this is concavity. So if the concavity is positive, we said then it was opening up. So this here is concave up. And if the second derivative is less than 0 or negative, then it's concave down. So you have a lot of things going on here that you need to know. What you must understand, first derivative represents the slope. If the slope is positive, increasing, negative, decreasing, constant. The second derivative is concavity, concave up positive, concave down positive. You must know this. Now, in using what we just got from the last slide, we're actually going to work backwards because I am giving you f of x. And what I'm asking you to do is graph f prime of x. Remember, that means the slope. And then I'm asking you to graph f double prime of x. And remember, that represents concavity. So let's first take a look at the function here. We're trying to graph slope. So what we know about slope is that slope can be positive or slope can be negative. If the slope is positive, because we're graphing the slope, if the slope is positive, it will need to be above the x-axis. So this will be above the x-axis. If the slope is negative, it's going to be below the x-axis. If the slope is 0, it has to be on the y-axis. Sorry, x-axis. So with that being said, we know the slope is 0 at the turning points. So right here at about -2, so I'm going to put a -2 on here. And right here about, it looks like it's about -0.75. So let's do this. Let's put a -1 on here and we'll go just slightly over. So we know at those 2 points, because we're graphing the slope and the slope is 0, it has to be on the x-axis. Now, if you look to the left of this, from -infinity to -2, we have a slope right here. The slope is positive. So if the slope is positive, it needs to be above the x-axis. So because it's above, it has to be coming down to this point right here, okay? Because this represents a positive slope, being above the x-axis. If you look between -2 and that negative 0.75, now we're below the x-axis because now our slope is negative. So if the slope is negative, we have to be below the x-axis. We have to come back to the 0 right here at that negative 0.75. I actually put it on 1. I said I wasn't going to, but and it's a positive 1, not negative. But we're going to go back to that 0 there. And then what happens is we're going back to having a positive slope. So now we have to be above the x-axis. So what we just did is we graphed the first derivative representing the slope. Again, everything above the x-axis has a positive slope. Everything below the x-axis has a negative slope. And everything on the x-axis is 0 slope. So now we're going to look at concavity. So we want to look, that's the second derivative of the original function. So we want to look back at that original function, and we want to know when it's concave up and concave down, and also when we have inflection points. So we know this part right here is concave down. We know this part right here is concave up. Now the point of inflection where it changes in concavity is going to be halfway in between there. So right about there. So the inflection point looks like it's about at -1. Maybe it's -0.5. So at that -1 or -0.5, whatever you think it is, the graph's small so it's hard to tell, that's where we have an inflection point. And remember on that last chart I gave you, that means that it is equal to 0. Okay, it's on the 0. When we have concave down, we know that that is a negative value. So a negative value would be down here. When it's concave up, so to the right of that -1 or -0.5, it's going to be positive, a positive value. So we're above the x-axis. Now, if you take a look at these three functions, originally I had a cubic function because I have 2 turning points, and the lowest degree it could be is an x to the 3rd. If you look at the second one, I have x squared, which should make sense because when you take the derivative of this, it drops a degree. The derivative of that would be 3x squared. There we go. Now, if we take another derivative, then we get x to the 1st, and you can see that that is a linear function. So every time you take a derivative, it should drop a degree. So that's just a good check to make sure that your graphs are on the right track with the graphs. Now I'm going to show you one more thing with second derivative as far as the algebraic part of it. So if you look at this first problem here, it says find the critical points of each function and determine whether they are relative maximums or minimums, and then find the point of inflection. So what we know about critical points, this goes back a couple lessons. Critical points are finding the derivative and setting it equal to 0. It's where the slope is 0 or it's undefined. So let's go ahead and find the derivative. So f prime of x. The derivative of this is going to be 12 minus 6x minus 6x squared. And I'm going to rewrite that in standard form. So I have my highest exponent first because I'm going to have to factor this. And now you can see I'm going to take out a -6. So I'm going to get an x squared plus an x minus a 2. Don't forget to change all your signs. That's why they both changed, the second and third. Now I'm going to take and factor this part. This factors into x plus 2 and x minus 1. And why I'm factoring it is because remember, when I'm finding the critical points, the slope is equal to 0. You can now see that my critical points are x equals -2 and x equals 1. So these right here are my critical points. And you write those as x equal. Now it says determine if they're maximums or minimums. Before, what we did is we went back to the original function here and we found f of -2 and then we found f of 1. And then the bigger number was the maximum and the smaller was the minimum. And you can still do that. That is acceptable. I'll just tell you what these answers are. This here is -19 and this one here is 8. So this would be a minimum and this would be a maximum. But I'm going to show you another way that you can determine minimums or maximums, and it is by finding the concavity. Because we know if something is concave up, well, then it has a minimum. So concave up has a minimum, the lowest point. If something is concave down, then it has a maximum right there. So we can also get a max and a minimum by concavity in the second derivative. And I'm going to show you that because we're asked to find the points of inflection anyway. The points of inflection, remember, is the second derivative being equal to 0. So I'm going to go back up to my first derivative, which is right there before I simplified. And I'm now going to take the derivative of that to get the second derivative. So this is my concavity test. Now I have negative 12x minus 6. And if I set that equal to 0, then what I'm going to know is that x equals negative 1/2 is a point of inflection. So I have a point of inflection, change in concavity at negative 1/2. So I'm going from concave up to concave down, or vice versa. Now the other thing you could have done to see which one, if this is a maximum or a minimum right here, is you could actually take the second derivative and plug in those values here, negative 2 and positive 1. And again, I don't care which way you do this. You're probably going to want to do it the first way, get it done with, and that's the way that you were taught anyway. But when you plug in negative 2, if you take this negative 2 and you plug it in right here for the x value, you'll get 24 minus 6, you'll get 18. When you plug in a 1, what you're going to get is negative 18. This can also show you concavity because you now know this is concave up right here, and you now know this is concave down right here. So therefore, you know that this here, because it's concave up, is a minimum. And this one here, because it's concave down, is a maximum. Now what I'm going to warn you is this. This, what we did before, we look for the biggest number to be the maximum and the smallest number to be the minimum. And it's the opposite with this because when you get a positive number, it's concave up. And remember, concave up has a minimum. And a negative number says it's concave down, and that says you have a maximum. So it's the opposite of what you initially were taught if you use the first derivative test. So again, you can use either one, but understand you will be asked at time to determine concavity, if it's concave up or concave down, and whether it has a maximum or minimum, and you cannot look at the bigger value to call it a maximum because it's the opposite. All right, and putting these two parts together, the last two problems here, the graph of the derivative is shown. Okay, so remember, if we're given the graph of a derivative, what it means is that we're given the graph of the slope. And we want to know what interval the function, so the original function, is increasing or decreasing. So again, we're given the slope. And if the slope right here is above the x-axis, our slope right there is positive. Anything above the x-axis. If the slope is positive, it means it's increasing. Anything that is below the x-axis right here has a negative slope. And if the slope is negative, it means the function is decreasing. So that's using that little chart, the recall thing on the first slide, but you're using it backwards. So where is the function increasing? Well, everywhere I have it in green. So it's increasing from negative infinity to, oh, here's my x-axis here. So negative infinity to 0. And then it goes back at 1, 2, 3, at 3 to infinity. I should probably put that, here's my coordinate plane here. Here it is here. Okay. Now, where it's decreasing is going to go from 0 to 3. And again, it's all parentheses because at those values of 0 and 3, you have a slope that is not increasing or decreasing because it's equal to 0. And then if you take a look at the maximum or the minimum, well, here's what we know. We know that this right here is a turning point, and this right here is a turning point. So one of these is a maximum and one is a minimum, because both of those places, the slope is equal to 0. So if we're increasing first, if we graph this, if we're increasing first, and then we have a turning point, and then we decrease, what we have right there from an increase to a decrease is we have a maximum. So we're going to have a maximum value right here at 0. Now the other one is going to give us a, right here, it's going to give us a minimum. And this is because we're decreasing first. So if we're decreasing and then we increase, that results in a minimum. So we have a minimum at the points of 3. So the maximum and the minimums are the turning points where it's at 0. And you just have to determine if they're max or minimums by seeing if we're increasing first or decreasing first or vice versa. So if you take a look at the next one, and maybe you can try this one on your own if you would like. We want to know where the function is increasing. So where it is increasing is where our slope is greater than 0 or positive. So everything above the x-axis. So it's increasing here to here and here to here. So it looks like it's going from -1 to 1, 2, 3. And then again at 5 to infinity. And the decrease part is the part that's below, so here and here. So it's decreasing from -infinity to -1, and also from 3 to 5 is also a decrease because the slope is negative. Now, at those 0 values, so at this point, and this point, the slope is equal to 0 because it's on the 0, it's on the x-axis. So those are going to be either maximums or minimums. So again, we have to think about what this graph would look like if we were graphing the derivative or the original function. So we're going to go from a decrease to an increase. So we're going to decrease and then increase. So this right here represents a minimum because it's a decrease followed by an increase. So that is a minimum at -1. If we look at 3, we have an increase to a decrease. An increase to a decrease is going to be a maximum. So we have a maximum at 3. And it better be a minimum right here at 5. And just to make sure it is, we're first decreasing and then we're increasing. Decrease to an increase does constitute a minimum. So we have maximums at x equals 4, minimum at x equals -1 and +5. I should have put x's on all of these because this is the x values of the max or minimum. So quite a bit of information there to regurgitate, pretty big unit. Ultimately, you need to know concavity, second derivative, slope, first derivative, and then being able to graph these ideas back and forth. And here's your homework for lesson 49. Goodbye.